Welcome to the Lecture 12, ContentFree Grammar. Chapter 9A, Syntax Analysis, ContentFree Grammar. Objective: we will cover the content-free grammar and also use it for the parser design. And it can be the LL parser, that is the recursive design parser design, and can be LR parser design, that can be table-driven parser design, and also the button-up parsing. So what we have in the previous lectures, we talk about the Lexer. So the Lexer's job is to tokenization. Okay, so this is a token stream being generated. Okay, and then next one, we need to use a parser to build it into some syntax tree. So the syntax tree will be something like this. Okay, so you would create such a syntax tree. And then this syntax tree can be evaluated. And in the lecture 8, we cover the recursive tree, and we talk about the in order and the pre-orders prefix, infix, prefix tree traversal. That you can use that for with the postfix traversal, and you can evaluate the result. So basically, here from the input, you create a token string, and these are covered in lecture 10 and 11 for the lexical analysis. So now 12 and 13, we cover the parser and how to generate the parsing tree, and then your program can be evaluated. So that's the total goal for us in this coming two lecture, the lecture 12 and lecture 13. And lecture 12, content-free grammar, will be more theoretical. We talk about a theoretical parser of different kind, and lecture 13 will be on the implementation side. So parsing one. So position of a parser in the compiler model, we talk about this. The lecture we talk about is generating the tokens, and at the same time, we build up the symbol table. And the symbol table is used to construct the syntax tree, and it may generate error. So this, we move on to chapters 12 and 13 on the parser side. Okay, so parser is the heart of the typical compiler, because tokenizer basically just create a symbol, but it doesn't involve the evaluation and also involve the computation. So parser really is the more important part. And as we described in the previous lecture, that some part of the lecture may need to have the input from the parser as well. So here, including the symbol tree, syntax tree, semantic analysis, these are very important topics, and parser is the heart of a typical compiler. So parser code the scanner to obtain the tokens of the input program, assembles the token together into syntax tree, and pass the tree to later stage for compiler. It can be used to generate call, or it can be used to evaluate the tree result and get the interpretation result. So parser will deliver the syntax tree, and then after that, it will be evaluation. And evaluation can be a compiler or can be a interpreter. So in effect, parser is in charge of the entire compilation process, and this style of compilation is sometimes referred to as syntax-directed translation. So syntax-directed means that you originally do not have syntax. Your data is like this. Okay, and you translate it into some sort of number plus number, okay, and then times a number, okay, and this plus sign here actually is an expression. So this number is also an expression, An expression times expression would create another expression. Okay, so here you have different expression or factors. Okay, so here basically the parser is involved with the grammar. Okay, so we call it a syntax-directed translation. So this is a whole idea of the compiler function. You have regular grammar generated lexer, content-free grammar generated parser, and in combine of these, we talk about the lexical analyzer and the syntactical analyzer, and the result will be a abstract syntax tree, and we create we decorate that tree with some value and error type and return value. You create a semantic graph. A semantic graph is a advanced version of the syntax tree, and it may have loopback. It may have loopback, so it actually is a graph. But this one is the what we use to evaluate the result or generate the code. So here, let's look at the parsing. Parsing is different from lexical analyzer. So lexical analyzer just look at the validity of its token, and we will decide that it is a ID or it is a number or it is a comment. And this one, the parsing will require the neighboring term to determine the grammatical position of that symbol. For example, you may have a.dat data, okay? So this one is a domain specifier, okay? And in other location, you may have that, and it actually maybe is the array index range, okay? And this one may also be a functional call. So this that, even the that can have different interpretation based on the grammatical condition. And also you may have 1 plus 1 plus 1. Your syntax tree can be plus 1 plus 1 this way, or it can be this way. Okay, so the way you parse actually may result in different way of evaluation. So that is very important. So let's look at our expression of the a times 2 plus 1. That are the token string. This is the token string we receive. So token string we receive will be product of all factor. Okay, this one you can say factor times a value. Okay, and then say plus 1. Plus 1 is a look ahead. You look into here and it's a look ahead. So this one you may pass into a tree that using the button-up passing. It will be a that actually is an ID. Okay, so here you have token. Time is actually is a symbol, integer for 2, plus is an operator, and then integer. So these are tokens. Based on these tokens, okay, ID will get the value and get the product, okay, and integer has the value and get a product, and then these two actually time together to create a product. Product sometimes people also call it vector, okay, so it's a vector. So this one, the whole thing is a vector. Okay, and factor actually is a sum. Sum is actually one kind of expression. So right hand side you have integer and value, and this one also is a factor. Factor is also expression. So expression plus expression, you got another expression. So here is the parsing structure you have. So basically from your token you got, you need to use the stack and then the symbol table as well to construct such parsing tree. That is the purpose of such parsing. And this one is an example of using LR parsing, button-up parsing. And we'll talk about the different parsing style later. So terminology, content-free grammar or push-down automata, this is the concept or the rule that used to build a parser. You need to describe the whole automata in the content-free grammar. And content-free grammar has terminal, non-terminal. Terminal is say ID, okay, ID say A, that's a terminal, okay. And 2 integer, that actually is also a terminal, okay. And time actually is an operator. And then the whole thing is a non-terminal. This non-terminal actually is a expression. And the ID by itself can be a non-terminal called vector. Okay. So in the previous slides, the vector is called product, but that's part of the non-terminal. So this will be described into your content-free grammar and production rule. So simple production rule derivation, that is the way that you actually do parsing. Okay, production is partition rule, and the end result is parsing tree. Okay, and we will also talk about sentential form. Okay, sentential form is the starting symbol S. So from the sentential form, how much can derive from S, that we call it the sentential form. So total number of the symbols that can be generated based on the starting symbol, that we call it the sentential form. So the possible outcome of the tokenization, we call it the sentential form. So here, these are the basic terminology for parsers, including the symbol production rule, derivation way, and the end result, and possible domain of your symbols. So sentential form. So sentential form is the starting symbol S of a grammar or any string. V union with T. Okay, star. V is your terminal. Okay, V is your V is your symbol, and T is your terminal, and the union of it, 0 or more, that can be derived from S. So starting S symbol, and you has B and AB and S, and these are the rule. Okay, this is the linear grammar. Okay, so S and B are non-terminal states. AB are terminals. S is the starting symbol, and these are the production rules. So based on this production rule, you get started from S. S can generate A and then S. Okay, and S can be B, so you can actually generate AS, and AS can generate AB. Okay, and B generate BB, so BB, so you can generate A, B, and B. Okay, B can be lambda. Okay, so you can actually terminate with A, B, B. Okay, or so these are different way that you actually derive your possible set. Okay, so all of the symbol or possible combination of the state, the set of these, we call it the sentential form. So that's the total number of the possible terminal and non-terminal collection that you can generate it from the starting symbol. We call it sentential form. Because this grammar is linear, so there's no recursion. So it just do linear derivation. So each sentential form has the most one variable. Okay, one variable. Hence, this never choice. There is never any choice about variable how to expand. So this one is only one way to do generation of the expansion. There's no different way of derivation. But in general, parsing is not this simple. Okay, this one is only a discussion for this sentential form. But not every grammar is linear grammar, and not every grammar can obtain such sentential form in such easy way. Okay, parsing. So by analog to regular expression to DFA, the deterministic finite automata, content-free grammar is the generator for the content-free language, and we so-called the push-down automata. And parser in general is a order of n cube problem. And this because it's order n cube, so really usually we do not go use the whole complete algorithm. Usually we may use a heuristic to make it faster. Okay, so there's an infinite number of grammar for every content-free language. Not all grammar are created equal. However, there are large classes of grammar which we can use to build parser that run in linear time. So basically, if you use all kind of grammar that can be described by content-free grammar, it will be this time. but we can limit it certain feature of those grammar. Then we can build parser that actually can run in runtime or basically unlock runtime. That actually is possible. Make the parser more practical. So it runs out. It turns out that for any CFG, we can create a parser that runs in order of 3 times. There are 2 well-known parsing algorithms that permit these. That is Early's algorithm and Cook younger Kasami algorithm, CYK algorithm. These are very old algorithms. They all can generate parser in order n cube time. And that's not acceptable. That actually is too slow. So that's the basic idea of parsing. Second, the parsing style. So parsing style, you mainly has a top-down parsing and bottom-up parsing. Okay. And fortunately, there are large class of grammar which we can build that run in linear time. These 2 types of the classes is LR parser and LL parser and LR parser. LL parser stands for left to right. So when you do parsing, it goes left to right and leftmost derivation. Or you can do left to right and rightmost. It's actually called R is actually buttoned up. Okay, so rightmost derivation. So LL is left to right, leftmost derivation. LR is actually left to right, but rightmost derivation. So what this really means is that if you have 1 plus 2 plus 3 plus 4, okay, this derivation, this parsing you can create. You can create 1 plus 2 plus 3 plus 4. This is LL parsing. Okay, you pass the first one first. Okay, you go deeper first. That's called LL parsing. Okay, and if you pick up the data to a step, then you can actually create 3 and 4. That you create a certain expression first, and then plus 2, and then plus 1. So you push this 1 and plus and 2 and plus and 3 and 4 and plus, and then you pop out this part, create this one first. This one using step, we call it rightmost derivation. So remember that actually LL is actually top down, okay, top down shape, okay. LRR is reverse, so actually it's bottom up derivation. Okay, so LL means left to right. That's actually the direction of scanning. Both LL and LR are actually left to right scanning. And derivation LL is leftmost, LR is rightmost. Okay, partial tree construction, LL is top down. Okay, top down, and LR is bottom up. Okay, and we can also call the LL type as a predictive parsing algorithm. LR, we can call it shift and reduce. Shift and reduce means you actually have 3 plus 4. We reduce it to an expression. An expression and the plus, we reduce that to further to an expression. So that's called shift and reduce. Predictive means that you have 1 plus 2. So we actually create 1 plus 2, and then we predict that will be an expression and save for later use. So that's called predictive algorithm. Okay, so these are basic terminology of 2 styles of the parsing, but these are not the complete description of different classes for parsing. As we say in the previous slides, there are several classes of the parser. Okay, there are several classes of the parser. There are several classes of parser, and some of them actually need the order of n cube time. Okay, and these are 2 main string methods we use. Okay, so parsing, LL parser also called top-down parser or predictive parser. LR parser also called bottom-up or shift-reduced parser, okay? And LR parser will also have some simplified version called simple LR parser, okay? It's a type of LR parser with small parsing symbol and relative simple parsing generating algorithm. This one is a easy way of designing a parser, but in general, most of the real-world compiler nowadays is not using this one. Okay, it's existing but not the most popular one. LR parser. Let's look ahead. LR parser. That is a simplified version of the canonical LR parser. This one, LR1, is very popular. Okay, very popular, and our Parser, Fresh Python are using it. Okay, so top-down parsing versus bottom-up parsing. So let's assume that we have a list of the ID. So let's assume that we are trying to print a list of A, comma, B, comma, C, comma, D. Okay, we try to print that. We have such a list. So here your ID list. So this one is the ID list. So ID list is a ID with ID tail. Okay, so I list will be ID and ID tail. And ID tail can be comma and ID, okay, and then ID tail, okay, and then ID tail can be the end. So basically empty, okay, something like that. So these are the rule. These are the rules. So basically to pass this list. To pass this list, you have A, comma, B, comma, C, comma, D. You can pass as A and then comma, B, comma, C, comma, D. Okay. If you have only single A, it will be only A, and follow the tail is actually empty. Also possible. This one we call it the top-down way of passing. Okay. And let's look at the other way that actually is bottom-up. So button up has different grammar. Okay, button up have different grammar, and button up actually for this one it is A, comma, B, comma, C, comma, D. So actually, you actually do grouping in this way. Okay, grouping in this way. So we'll discuss that later. Okay. So top-down LL parsing. Okay, so basically you group your data in this way. So you originally think that it is your ID list. So ID list that you check your A, comma something. Okay, so you predict that it is an ID A and then with some tail. So you go from top down. Your A, B, C, D. You go from top down, and you determine that's the A, and then there's a tail over there, right? So A determined, and then this ID we actually find out is a comma B over there. And we determine that maybe another tail. So comma B and A, and then we determine A, comma C and tail. Okay. And then it becomes A, comma B, comma C, and the empty list. Okay. So basically that actually is top down. So top down you actually do prediction, predict which type of the symbol you would generate. Okay. And bottom up is different. Bottom up actually is you have the A. Okay. So you push in your A. You have the A comma, push it comma, and B, and then B comma, C comma, and then you see the end of that, right? You see the end of that. So you find a rule that says a comma, ID, and then the empty list. So this one you determine that it is the ID tail. So based on this ID tail, you actually predict another level, and then you predict another level. So this one is just like you popping out things from your stack. So we call this one as the bottom-up parsing. So these are two ways you can do parsing. Canonical deviation. At no point does the bottom-up parser predict what it will see next. So it basically push in every data, and when you see everything, it start to build things from bottom up. So rather it ship the token into the forest until it recognizes right-hand side, and it start to reduce to the left-hand side. So this is called ship and reduce, or push and pop, okay? Push and pop style. It is ship and reduce. Because of this behavior, button-up parser are sometimes called ship reduce parsers. Moving up the figures from bottom to top, we can see that the ship reduce parser trace out rightmost deviation in reverse, okay? And because of such button-up parsers, the first to receive careful formal study rightmost deviation, sometimes called canonical. Okay, it's also called canonical deviation. And one set of grammar, you can even use different way to derive it, with the help of stack, okay, or you directly go prediction that will create different type. That will create different type. So next one actually is the building space with button-up grammar. So you can multiply the grammar as the button-up grammar as this. You have the ID equals ID tail with comma first, okay? And then you have the ID prefix and ID prefix comma ID. And ID prefix can also be an ID. So this is a modified grammar only for button-up. And this one doesn't fit to the previous one. So your grammar can be designed in this way or in this way, two-way. This one can be used for top-down and button-up parsing. And the one we show on here can only be used for that button-up. Okay, can only be used for button-up. Okay, so parsing, every LL1, okay, LL1 is actually one look ahead. So the one means the number of the look ahead, okay? So LL1 grammar is also LR1 grammar, okay? Even though they do prediction and the push pop in different way, but the grammar can be the same, okay? Grammar can be the same. Though the right recursion in production tend to require a very deep stack, okay? So LR need to have deep stack and complicate the semantic analysis. Every content-free language can be parsed deterministically has a LSR1 or LR1 parser. Okay, every content-free grammar can be done with that. Every deterministic CFL with prefix property, a string is a prefix of another value string and has a LR0 grammar. LR0 grammar is a grammar without. This zero means no look ahead type of the grammar, okay? And this one is very spatial and very limited power. But if your language is deterministic means that it do not have different way of interpretation. There's only one way of interpretation. Then that's called deterministic content-free language. So parsing, LR1 parser with one token look ahead, okay? So the one is one token look ahead. You commonly see LR, LL or LR with parentheses and some number in there. This one, with the number indicated how many tokens of look ahead are required in order to pass. Almost all real compilers use one token look ahead. Okay, so basically, even though that's possible to have more, but more real compilers are using one look ahead. But the power of look ahead with 3 or 4 or even infinity will be more powerful. It will be the full set for the LR parsing. Okay, so the expression grammar you saw before is LR1, but not L1 parser. Okay, so basically here we have an example of LR, but not LL. Okay, LR actually you allow the lab, the so-called lab recursive. Okay, you directly call this one that actually is okay, but the LL parsing do not allow the lab recursive. Okay, do not allow the lab recursive. So this one you do have a lab recursive with the turn over here. you will call the turn. Okay, so this one is a LR passing. And you have expression. Expression can be turn or expression at operator turn. Okay, or you have the turn. Okay, and turn can be a factor or turn multiplied with factor. And factor can be ID number, okay, or number or minus factor or parenthesis expression. Okay, so factor is a single multipliable item. And add and multiply two label of the operators. So here we have a type of parser. Our parsing have top down and bottom up. Bottom up, you have shift reduce LR parsing, and LR parsing you have SLR parsing, normal LR parsing, and look ahead LR parsing. And top down you have recursive descent, backtracking, and non-backtracking. Non-backtracking, you have the predictive parser and LR parsing, LL parsing. Okay, so mainly the top down you have predictive parsing, and you can be recursive descent or predictive parser. Bottom up, you have shift reduce or push and pop type style, and they are SLR, LR, and LALR type. Okay. Section 3, parsing 3, recursive descent parsing. Top-down grammar for a calculator. So here we have a set of LL1 grammar for simple calculator language. So a program is statement list, a collection of statement lists. A statement list is a statement with a statement list. And statement list will recursive calling itself or nothing. A statement can be a ID assigned with some value or read some value or write some expression. This is called a statement. Statement, we have three types of statement: assignment statement, read statement, and write statement. And the expression can have turn and turn tail. Turn tail can have add with turn and turn tail. And turn can be factor with factor tail. Factor tail may be multiplied with factor and factor tail. And factor can be a parenthesis with expression or ID or number. And then add operator can be plus and minus if you are in the turn. And multiply can be multiply or division for the factor tails. Okay, so these are actually the so-called LL1 parsing algorithm. And this one, as you can see, there is no left recursion, So it's a top-down predictive parsing. The calculator allows value to be read to name variables which used in the expression. Expression written to the output. Control flow is linear, so it's actually control flow is linear. There's no loop, no if statement, no jump in this simple language. And the end mark is to finish the programming, the scanner. Okay, the whole thing will be stop. Okay, and in regular expression, we use the symbol epsilon to denote the empty string. So this one is an empty string. That's called epsilon production. So anyway, this is a language, and it's a special language designed for LL1 language for calculator. And we are going to show how parser work on this case. So recursive descent. So basically, this one, we have this expression, this language, and we can further simplify to this simple one. The figure 2.16 and 2.18, these are the number used in the textbook of the programming language programmatics. Okay, so if you are interested, and remember these numbers are for the version 4, not version 3. Okay, so these are the grammar. So basically, let's assume that we have such a token list. Okay, token list with token 2, token 5, token 6, token 8, and token 9, and we are doing top-down parsing, build a set of mutual recursive procedure. The structure of the resulting program closely mirror the grammar that recognized in here. Okay, so the parsing tree will be built. So this one is to show you how to design a parser, and this parser is recursive descent parser, and it requires the LL1 algorithm, LL1 parsing algorithm in order to work. Okay, so here let's look at this one. Consider that we only have two rules: expression equals term or term plus expression. So recursive. Term can be integer or integer times term, or a parenthesis with expression. So our input is this parenthesis int and parenthesis. So let's look at this one. Okay, for example, this one can be an example of parenthesis 2 and parenthesis. Okay, so that's actually look how this recursive descent can go through this whole thing. So first one, we see a parenthesis, that's the token we see. Okay, and we are trying to use an expression. So we try to use expression rule, and we find out it's a turn. So we try turn, but turn will be actually turn. We try turn, and try turn. First one is integer, so integer we try. Okay, but it is not integer. It's not integer, so we backtrack. So it's not integer, we backtrack. Backtrack, we try the second rule. Can it be integer times turn? Okay, we try this one. So the next one we will see will be actually will be integer times turn, but we have parentheses. So apparently it doesn't match. So we go up again, backtracking. So backtracking, that's why we try parentheses in, with expression. So parentheses with expression that's actually correct. So we try to validate if the integer is actually a expression, so we try. So we advance. Advance, we go to the rule for the expression, and we check out it's a turn. We check out it's a turn, and actually the first one we test it means an integer, and it match. It matches, so we actually go back. Go back, we try the next token, that would be a parenthesis, and it match again. So we go back. So that finished the parsing process using the recursive descent. So here, let's actually look at it one more time. So the so-called recursive descent is like, we got a set of grammar, and we keep trying, and if it rejects, we try another one. So we keep trying different possible evaluation based on the grammar rule, and we try one by one. If no match, we go back. If no match, we go back. So that's called recursive descent. So it's a recursive call of many validation function, and then if not match, we roll back. If not match, we roll back. Okay, and you may go down to several level and then go back. So basically, this recursive descent example is you do scanning, but at the same time you are doing parsing at the same time. Okay, so basically this one is if you had the input, okay, and you tokenize it, okay, tokenize it in this format, and you try to build a syntax tree, okay, and here you actually will pass the structure of the expression into subtree, okay, and you will move on to the next one to pass another subtree. So basically the whole statement is passing to such a tree. Okay, so that actually is the so-called parsing. Backtracking, when syntax function fail, we want it to have no side effect. So we need to clean up whatever we have tried. So we want the input to be exactly the way it was before calling the function. So we clean that. That's called backtracking. Because this makes it easier for other functions to have a goal at the passing at the same input. In addition, the function should delete any object that it created. So need to restore back to the condition that it has. That's called backtracking. So backtracking, you need to have the backup procedure for every function call. In other words, the function have to backtrack to an earlier situation. That's called rollback. Section 4, parsing 4, building a recursive descent parser. So this one, okay, we want to build a recursive descent parser. So how do we parse a string with our calculator grammar? We can formalize this process in two ways. First, to build a recursive descent parser whose subroutines corresponds 1, 1, 1, and to the non-terminal. So basically, every token or every turn, it match a rule. Okay, every token, every rule, every expansion, every grammar rule, you should have one function call. So right here you have option. So the option you can actually split it into two separate lines. Okay, you should split it into two separate lines. Okay, you should split them into two separate lines. So this is not 5 rule. It actually is a 2. Okay, this one is actually 2. Okay, this one is 3. This one 2, 2. So totally here we have 10 actually 11 different rules, and you need to write 11 different production rule code. Okay, so that's actually 2 parser way you can build a parser. One is using the so-called recursive design. The other one is table driven. Table driven is based on you push in your data and then you later find a rule to apply for it. That's called table driven. And table driven usually is used for button-up implementation. LL grammar can also use table driven. So we will describe the table driven later. At this moment, let's look at the recursive descent. Okay, table driven is like this. You pass the input and you will push some turn to the stack. Okay, and you need to have a passing table. So this one we'll discuss it later. Okay, so recursive descent parser for the calculated language. Pseudocode is in 2.17. Okay, and it has a subroutine for each non-terminal grammar, and it has a mechanism like input token to inspect the next token available for the scanner and subroutine to consume and update this token, and the process verify it is one that expected. Okay, so that's something that we actually need to go through every function call for it. Okay, so this one is a grammar. So your top level, you have a function called match. Okay, it's a match function, and there's a program. So you start program, and program will call the statement list validation and the end of program validation. So you will match this one and actually also look at the so-called statement list. And statement list, you will take the token and match with a statement or statement list. Okay, and statement, you have the ID and read and write, 3 different possible way you can do. So statement, you have the ID assignment. Statement, you can have the ID statement, read and write. So you use the look ahead to predict which one you should go. So for example, if it's actually you call the statement evaluation. So statement evaluation is over here. An ID, you use the matching ID way. If not, you actually will cause the evaluation error and do backtrack. Okay. So here it shows you every single function's pseudocode for recursive descent procedures. Okay, that's actually using the LL parsing. So like the button-up grammar, this one capture the associativity and the procedure, but most people can find it pretty. For one thing, the operand of a given operator are in the right-hand side together. Okay. However, the simplicity of parsing algorithm make up this weakness. So basically, LL parsing with the recursive descent is actually simpler, but because it need to do a lot of backtracking, so actually it takes some time. Okay, so LL parsing, if we have this one, okay, it is example, then we will pass the tree in this way. Okay, that's the parsing tree for this simple program. Okay, that's a result of recursive descent. So let's look, read HFB or recursive descent parser with tool. So basically here we have a simple calculator, the P1 recursive descent parser. So actually you should find that there's a recursive descent. Okay, there's a folder called recursive descent. In this folder, there are 3 files: calculator, lex, and also pass. Okay, 3 functions. Calculator is top level. Okay, so it actually is a very simple Python code, pretty decent performance for the calculator language or and for using the recursive descent parser. Okay, so actually pretty error message. Okay, and self-modifying parser and lexer, and lazy parsing support for iterative use. Okay, so it's a very simple calculator example called calculator.py. The lexer is constructed with a list of tokens and regular expression with the Python regular expression syntax. Okay, so the parser works by translating the EBNF-like grammar directly into recursive descent parser. So calculator.py is calculator language token table. Okay, and BO lexer names lexer and our token table. And calculator language parsing rule, you will have that as well. And BO a parser. Okay, and there is a re-evaluate, print, and look back. Okay, so let's look at the program now instead of just talking. Okay, let's look at the program. So here, let me actually open the folder. Go into the, you can download this chapter, lecture 12 program. There's a recursive descent. So there are 3 files, calculator, lexer, and the parser. So let's look at calculator. So the calculator actually what? It import the lexer. Okay, lexer is this one. Okay, it's not pre. Okay, it's not using the pre. It actually is using its own design. Okay, lexer and parser. Okay, and you also import the decimal. So right here we do have the table. This one is a simple table. So each token's type, okay, and the dual, the regular expression dual we put into the table, okay, and then we build a lexer. So lexer actually is using the lexer constructor in the lex.py. So here we do have the token class and lexer class. So from this token lexer class, and there is a building the lexer. Okay, building the lexer. There's a lexer function of build the lexer. Okay, so going back, it will, you set up this and you put the table into the lexer. A lexer will create a lexer and to in here. Okay, and here we have reduced function for the binary operator. So here we have the rule table. Okay, rule table is actually is a so-called rule table for the production rules for the ContentFree Grammar. Okay, so atom is actually a single ID, a number, and then references expression reference. So this one actually you give the value over here. Okay, you give the value over here, and a factor or atom powered factor. So power is raised to the power. Okay, and it can be these. Okay, and atom. Okay, and this one is a factor. Okay, and it can also be a atom. Okay, and it actually can be minus factor. Okay, these are rules. These are rules. Okay, so these are rules, and you parser set the rule and make sure that your type label is actually an expression. So you start evaluation from expression. Okay, so that create a parser. So with the parser and lexer, what you will do is actually going to here where true, your line is empty, and you will prompt something. Okay, prompt something, and then you get the input from prompt. Okay, and then you basically put the line to create tokens, and the token being feed into parser and get a result. And so this one is the REPL part. So let's look at the terminal right now. Okay, so right now we are in the recursive descent. So here let's run this one. Actually, it's called Python. Okay, calculator py. So we bring up this greater than. Okay, and that actually okay, and it will look at the line. look at the line. You will look at the line. While true, you look at the line. So line will actually get the input from prompt and then put into the line. So let's do this one. Let's have this 3 plus 3 plus 4. Okay. And then times 2. So this one is a line, and that line will be passed to the token, and the token actually will be actually generated by to token, and the token will send into the parser, and parser will get this 14. Okay, so that actually is the 7 times 2, that's 14. Okay, so we do have this different term that you can use. Okay, multiply different set. So here it only allows the number, but it does not allow the symbol here. Okay, there's no symbol, no ID can be used. Only plus, minus, divide, and power. So let's try this one. Let's do power. So 2 cap 3 HA. That's a power. Okay, there's a power. So let's try 3.544 times 2.233. Okay, that's actually this one here. So this one show you it is a this one is a so-called recursive descent parser. So the next portion is a tokenizer. Okay, this one is a tokenizer, and you will take the table of tokens and create the lexer. Okay. And then there are production rules, reduction rules, and those different rules will be passed to this parser. So this parser is a so-called recursive descent parser. Okay, this one is in this parser function. Okay, but the program is really huge, so we do not have time to go over it line by line. You can study by yourself. Okay, you can study by yourself. So over here, we have a calculator. It has created a table and then feed into the lexer, and then create a rule, and then feed the rule and the token list to the parser. You create a parser, and then you put the type label to be an expression. Okay, so this calculator parser, it is an interpreter, but it can only process expression. There's no function code. No statement. Okay, it's only expression. Your evaluation. So this one you can look at it as an evaluation loop. Okay, so this one is the code we saw a moment ago. Okay, and lexer have 2 more class. Lexer error class that actually give you the error message and info for the lexer's current file name, file number, text position. It is similar to the so-called flex tool. Okay, and then these are the classes, and then parser you can see the pseudocode, and when you run, you just run Python calculator.py. So that concludes our talk for this recursive descent parser. Section 6, LL parsing. So we finished the basic theory introduction for different parser, theoretical parser design. So we are moving on to the LL parsing, LR parsing, LL parsing, and also LR parsing. So these are detailed theoretical study of different parsing style, including LL parsing. This discussion, the table-driven way of designing parser for LL parsing. Also, table-driven way to design the LR parsing. So in this lecture, we introduce the so-called parsing using recursive descent for LL parsing. Also, table-driven way of parsing for LL and LR way. So now we are moving on to our section 6, writing an LL1 grammar parsing. Now, let's look at the grammar effect of the LL1 grammar and the parsing for using the table-driven parsing for LL1 grammar. So writing a LL1 grammar, if you use the recursive design parser, then it's fine. We already described it. But if you want to use the table-driven design for parser, then you actually need to follow certain rules. Okay, so when designing the recursive design parser, one has to acquire a certain facility in writing and modifying LL1 grammar. These two common obstacles are the LL1ness or left recursion and common prefix. These two will create trouble, left recursion and the common prefix. This one, two are actually the main problem come from, okay? So you need to transform your grammar from a non-LL1 compatible to LL1 compatible way, okay? So you need to eliminate the left recursion and try to factorize so that you remove the so-called common prefix. Okay, so left factorization and elimination of the recursion. So a grammar G is LL1 if actually A produce alpha or beta are two distinct production rules. Okay, they are two distinct production rules. For no terminal, both alpha and beta derive string beginning with A. Okay, at most one of alpha and beta can derive empty string. Okay, so beta actually go to T, then A does not drive any string beginning with terminal in the follow set of A. This portion we will study later. Okay, we'll study later. So now first is left recursion. Left recursion, we say that a grammar is left recursion if your production rule say ID list prefix will generate ID list prefix right away. This one will create some trouble. Why? Because you have some rule. So that's rule one. Rule one, you actually create some non-terminal symbols S. And this S, you kind of look into the S rule, and S rule call the S right away. Then you actually become what? Recursive call. Keep calling, and actually is what? Infinite call, infinite recursion. So basically, you have the left recursion. You call this, and you will call this right away. Call this and call it right away. So actually, you create the infinite recursion. So you will eventually have the stack overflow. So left recursion, if you have such a dual, A produce A alpha, okay, it won't work. It has a left recursion rule. So this one, we don't use it. So we actually change the left recursion to the right recursion rule. So basically, originally you have the A comma, A comma, A comma, A. So we say you have the prefix and comma D. Okay, this one's comma A, comma A, comma A. This one we should transform to a different rule that actually has, you will have the A comma A comma A comma A, and you create A comma A comma A comma, okay, and the A by itself. So A by itself, basically you actually, if you use this rule, it won't work. Okay, you have to convert it to this style of the rule. You actually have a separate ID first, and others are ID tail. So ID tail, you have the comma D, comma D, comma D. So this one will work. Okay. So right recursion, this one's right recursion. So you have A, comma B, comma C, comma D. You A is matching this one, and comma B, comma C, comma D. This is right recursion. Left recursion, you use this one, A, comma B, comma C, comma D. You use prefix and the comma B. This rule, it will go into endless recursion. So that recursion won't work. So you have such transform you can do, okay, from this grammar rule to this grammar rule. Common prefix. Common prefix is that you have ID, but you have two things actually will use the ID. Okay, two rules that actually start with the same ID. This will actually create trouble because you don't know whether I should try the first one or try the second one. Okay, so common prefix occur when two different production rules with the same left-hand side begin with the same symbol. Okay, a left recursion common prefix can be removed with grammar mechanical. So this one we can kind of factor it out. It's just like you have S create A and create AB. You can create S and then create say A and then with K, and K will create A and K will create B, something like that. You can convert it in this way that will actually move the problem. So here like this, you have this A, you create A and A and A, B, A and B, and A create A and C, okay, and you create A and that will have the edit state B, and B will create B and C. This one is called factoring out the common factor. So you put the ID here and generate a new symbol called statement list tail, and then you can put aside with expression and the argument list. This is factoring out the common factor. So there are infinitely many non-LL language, okay, and the mechanical transformation work on them just fine, okay. The few that arise in practice, however, can generally be handled by heuristic. So here you have to understand that the non-LL compatible language is not just these two rules. There are more rules that can create it, but in fact, most of them can be handled. Okay, can be handled. Passing the dangling else. Okay, the best known example of non-LL construct is so-called dangling else. Okay, so dangling else happen that if C then if C2 then S1 then else S2. So we don't know this then. Okay, so basically this one is this one actually the then belong to this if. Okay, this else belong to this if. Okay, else belong to the closer if. This one is an else that we don't know whether it belong to the first if or second if. This is called the dangling if, dangling else. Okay, so dangling else, when we have a statement that actually produce if condition then close and else close, and this may happen that we may have situation that we don't know our if, okay, condition, and then if condition and else, and then doing something. Okay, so here if we have something like this, okay, if we have something like this, we actually don't know which if it actually belongs to, especially when we have single statement, we do not have a curly brace, we actually don't know this one should belong to this one or this one. Okay, we actually don't know. And this one can be solved by require them into the else belonging to the closer if. So we modify the so-called grammar in this way. Statement create a balanced statement and unbalanced statement. So balanced statement will match the if then else first. So with this one, you match the else with the closer if. You don't consider the unbalanced one. Okay, you don't consider the unbalanced one. So you create a balanced one first. Okay, you create a balanced one here. By doing this, actually you will be able to you consider the balance first, and balance will check this one first. So you will create the local one, and the other one become an unbalanced one. Unbalanced one. So unbalanced one is being processed later. Okay, so this one will remove the ambiguity. So that will remove the ambiguity of it. Okay, and there are some other things that the usual approach, whether top down or bottom up, is to use the ambiguity grammar together with these ambiguity rules that says else go with the closer than. Okay, so this one actually is the removal of the ambiguity. And M mark for structure statement. And you can also use the M mark that will, some language use M mark, some language force you to use the curly brace. That will also help in reducing the ambiguity. But they come with a penalty. If the language does not design well, you will end up many parentheses or many end at the end. Okay. So some language like Python, we use some style more similar to the right-hand side. Okay. That remove the need for having multiple end. Okay. So that is also an issue to when you remove the ambiguity, you can have different way to handle it. Adding the MR is good, but sometimes it actually also creates a trouble. So now let's look at the table-driven top-down parser. This one a little bit more technical. So section 7, overview of table-driven top-down parsers. So we have the recursive descent parser. Now we actually look into the table-driven parser. With the help of a stack, we will be able to do top-down style, LL style table-driven parser. Okay, it will create code. And we need to build a parsing table. Okay, parsing table provide the transition of the rules, transition of the rules. So there are 4 kinds of the rules in there: empty rule, epsilon rule, epsilon set, predict set, first set, and follow set. Okay, we will explain this. So table-driven LL parsing, you have big loop in which you repeatedly look up an action in 2-dimensional table based on the current leftmost, the non-terminal, and current input token. The actions are matching terminal, produce a production, announce a syntax error. So driver and table for top-down parsing. In recursive descent parser, each arm of a case statement, okay, that actually each arm of case statement corresponding to a production, okay. And here we are using the table-driven way. Then we need to match a terminal and predict a production. So the table need to include this, okay, and announce syntax error when there's something wrong, okay. So at any given point in the parsing, you consider the code beyond the program counter in the parsing routine, and it's actually need to have the call stack. We obtain the list of symbols that the parser expect to see between here and the end of the program. A table-driven parser maintain a split stack, okay? So anyway, this is a little bit very theoretical. So it actually comes with the help of the stack. So here we have the pseudocode for the table-driven LL parser. So basically, you have a set of terminal and non-terminal and symbol and rule, okay? And there's a parsing table. Each parsing table, you have terminal and non-terminal, okay? And it's action and production. So there's a table. There's a table for the transition. And there's a stack called parse stack, okay? And then you actually start your program by running the loop. So you actually will actually see a symbol from the stack. You pop out something, and if the expected symbol is a terminal, you try to match the terminal, okay. And then if the symbol is end of the program, we finish, okay. Otherwise, we actually try to go to the actually what? Go to see if the past table, look at the past table. Is the past table with the token type is actually an error. That means that there's no match. No match means that you have passing error. That means that you pass fail. Otherwise, you bring up the production rule and continue to actually continue to run it. Okay, so basically, what this one say is that we have a program and we look at a say ID. ID will have the rule number one. It actually is a statement list. So statement list can have ID, can have read, can have write. So those are statements. So you go to statement and go to statement. So this one is 0, 1, 2. So statement can have 4, 5, or 6. 4 is the ID assignment. Okay, so 4 rule 0, 1, 2, 3, 4. So you go to here. 5 is actually here. 6 is here. Okay, read and write. So those are actually state transition that been assigned. But in the dash line means that the current token you end up should be wrong. Okay, you will be wrong. So that's the table. That's the table. But if you based on that table, of course you know how to do parsing. But now the question comes is that how you can design your table. Okay, the table design is actually a problem. So table-driven way you actually do program. Okay, let's assume that we are processing this one. This one actually we are looking at the sum and average program. So sum and average program actually we see it a moment ago. Read A, read B, sum equals A plus B. Write sum divided by 2. Okay, this is the so-called sum and average program. So this is sum average program. Okay, so we have read A. So we have read A and read B. So read A, we actually start a step. Okay, and we predict a program. So program C statement list. Statement list is the three statement. Statement C read A, right? Read A. So right here we do go into read A. Okay, we match read, we match A, right? So and then we match the statement list with the statement and statement list. Okay, so statement we have the read A, and then we actually go into the read B portion. So read B we have separate statements. So actually that's done. Okay, and that next one we have the assignment. Next one we see the ID. So read A, read B. After read A, read B, we do have the assignment. We do have assignment sum equals A plus B. Sum equals A plus B, we go down to the parsing. So we have the ID, that's the sum, assigned with A plus B, so it's an expression. Expression go term, factor, factor tail. So factor, you see A, okay, A, and then factor tail is epsilon. And add up is plus, you match plus, and you match B, okay, and turn back, and then next one you go to the right expression. So next one you see the sum average program. Sum average program, you finish this one, then you write sum and write sum divided by 2. So these 2, we go down to here, it actually is right expression. The expression right after expression, the expression is actually sum. So factor ID and you finish, okay? And then you have the right expression. Right expression, you have the sum divide. So sum is the ID and divide, and there's a number and you finish it. So basically the whole parsing program end up with such result. And this one is the parsing tree using the table-driven way to pass this program, okay, pass this program. And the step are using, not using this in recursive descent, but it actually is using the so-called table-driven way, using this table, okay, using the table. And every time you have the state and the possible input token to generate it. So that is the parsing process. But here comes the problem of how to create a table. Okay, so now the problem is that, okay, it's good that you actually can use a table to create the transition of the state and statement. Okay, and how can we automatically generate the so-called table? So here we have the four set: epsilon set, first set, and follow set, and predict set. Okay, so we need to have these different predict sets. Okay, so basically it's a first step for each symbol. So first step for each symbol is that for that symbol you see there is some first possible terms, and follow set means that someone will follow me. Okay, someone will follow me for non-terminals that will come after me. And there's a predict set. Predict set means that there's a rule that may be predicted by me. Okay, so these are the so-called set. So set definition. So we have content-free grammar in PNF. Okay, and they are first set, follow set, and predict set. Okay, so each set is a symbol. Okay, so first set is the set of tokens that can appear as the first token in expansion of A. When A expands, the first token that can be is in the first set. Follow set is the set of tokens that can appear immediately after A. When A finish, you should see a follow set. That is for the look ahead to determine which rule you should use. Predict set means that a set of tokens that can appear in a very passing string that can derive from by its prediction rule. Okay, this is actually very vague right here. You can mathematically describe them like this. Okay, but we do not need to understand this math. Let's continue. Okay, so for top-down parsing, only set that we need is predict set. Okay, it turned out the first step is not necessary to calculate the predict set. So we actually just need to use a predict set and the follow set. That is actually more important. Okay. And epsilon set is that which symbol we create epsilon. That's epsilon set. So epsilon set contain all the non-terminal which can expand to empty set. So which will cause no operation. That's called epsilon set. This one sometimes can be used for extra state. Okay, so extra state stopping. But more important would be the predict set and follow set. So predict set, you have a symbol on the left. If there's a token on the right, okay, then you add that token into your A's predict set. Okay, if on the right there is another symbol, non-terminal, the whole predict set of the B will become A's predict set. Okay, if there's an epsilon set that actually belong to after A, okay, then the follow set means that, okay, A will create epsilon, okay, will create epsilon. So current symbol, you see a current symbol A, then there may be some label following it. That's a follow set. Then that one can be the next symbol that I will see. So that's called follow set of the A. Follow set of the A would be also the predict set of the A. Okay, so these are three rules. Remember, these three rules would be very important when you create the predict set. Okay, when you create this predict set. So basically, predict set is the set of the tokens that A may use a production rule to go to. Okay, that's called predict set. And follow set is the symbol that may follow the symbol A. So here there is a rule C will produce A and token. So token will follow A, then we will add that token to A's follow set. And B actually is a non-terminal, follow A, then the predict set, rule production of the predict set B will become A's follow set. So if B actually go a very long way, and then A is at the end of B, then B's follow set will be also A's follow set, since A is the last symbol for B. Okay, so these actually create, these are the three rules to create predict set and follow set. Okay. Now, with the predict set and follow set, how can we build a table? Let's look at a simple calculator language. So we have a statement, okay, starting symbol. So start symbol will be expression, then stop, okay. An expression can be turned with expression tail. Okay, expression tail will be operand, adding operand, addition operand with term. So term plus term, that's expression tail. And term tail will be factor and term tail. So it's operand, multiplier, operand, and factor and tail. So it actually is factor. S factor is starting factor. Starting factor can be operand factor or factor, the minus or plus. Okay, so that's something like that. Okay, that's minus or plus something. And factor can be number or parenthesis expression, right parenthesis. So these are the rule for a calculation rule. Okay. So these are the rule for the calculation rule. This basically define factor is number or parenthesis expression. Okay. Starting factor actually is plus minus factor or factor. Okay. This turn actually is starting factor. Actually multiply or divide another factor. Okay. And then expression is actually with the turn plus turn. Okay, so these are the basic rule we simplify on the right hand side. Okay, for the calculator language that we look at. Now epsilon set is empty, and we have this different non-terminal table, and we try to create the predict set and follow set based on this grammar rule. Okay. So let's look at the epsilon set first. Epsilon set, this one was created, this one was created. Okay, so there are two symbols that were created. So basically, it's actually expression tail and term tail will create these two. Okay, so that's just apply that. And then epsilon set is actually decided. Now this one we actually will copy the predict set. So predict set is that using the prediction rule, the first set token will be put right away into the predict set. Okay, this actually just do that. Okay, so this one is actually applying. This one is applying the predict set of the production rule that is the first rule one here. Okay, applying the first rule one here. And you will create the table. You'll create a table like this. Okay. So we get that. So we had a predict set. So we have a predict set. Then we can look at the so-called stopping the follow set. Follow set, you actually applying the rule one for follow set. So rule one for follow set is any production rule that you have the non-terminal followed by token, you put that token into there. So that is the follow set. So this follow set is that you have the ESP with stop. So stop should be the ESP's follow set. So there is another left right side parenthesis that is also the follow set for expression. So you look at the right hand side, see who has the symbol that follows some non-terminal. So we finish that. Second one, we finish that. Third one, we will use the rule 3 for follow set. Rule 3 for follow set saying if the follow set, if a non-terminal is the last one for another non-terminal, the follow set of B will go to follow set of A. So basically, this expand tail is actually will take over the expressions over follow set. So just copy down. This is rule number 3. Then Then we will use a predict set rule number 3. Prediction set rule number 3 saying that actually if A go to some empty set, okay, then the follow set of the A will be added to the predict set of A. So A, someone who actually go to the empty state. So here actually we see the expense tail, okay, and then this one has the epsilon set. Epsilon set, you had that, then your follow set should also be your predict set. So copy that to your predict set. Okay. Next one, apply the rule 2 for follow set. Rule 2 for follow set. Rule 2 for follow set means that if there is a non-terminal following your A, then the predict set of the following terminal should be your follow set. So here, let's see. Here we have S. Okay. Let's see. This one we copy. Okay. Then next one. We have a expression will go to turn, and is expression tail. So expression tail followed by the follow turn. Follow turn. So basically, if follow turn, so basically the prediction set of the expression tail will be the follow set or turn. So we copy the expression tails set to the follow set over here. And the next one using the rule 3 for follow set to the turn tail. So here the rule number 3 saying that, okay, this one is the tail, the last non-terminal is the here. So basically this one's follow set should be the same as should be assigned, terms of follow set should be assigned to the 10 tails follow set. So you copy that. And the next one, actually, you will see the predict set numbers rule 3. Okay, prediction rule 3 basically is saying that, okay, turn tail generate the epsilon, then the so-called follow set of the A should also be assigned to the predict set of the same non-terminal. And then next one we apply the rule 2 for follow set. Rule 2 for follow set saying that, okay, a non-terminal rule set for follow set rule number 2, okay. Follow set rule number 2 saying that, okay, if there's a rule that actually two non-terminal, another following one, the predict set should be assigned to the preceding one. So follow set. So this one, the follow set of the S vector. Okay, follow set of the S vector. Follow set of predict set of the turn tail should be copied to the follow set of S vector. So predict set of the turn tail should be copied to the follow set of the S vector. Same thing, predict set of the turn tail should be copied to the vector. So we finish these two. Okay, next one we use the predict set rule number 2. Predict set rule number 2, actually go back to predict set rule number 2. Predict set rule number 2 saying that if A predict B, then B's predict set will be A's predict set. So it's a sum follow rule. Sum follow rule means that the predict set for expression should be copied to S. Should be copied to S, solution copy to this. Okay, so we need to go from bottom down. So basically here you have the factor. Factor has num and the LP copy to S factor. Okay, and S factor will be copied to turn. And turn will copy to expression. And expression will copy to the starting symbol S. Okay, so this one actually should go bottom up for this rule number 2. Okay, so this is the final table that we create with if, epsilon, and predict and follow. Okay, predict and follow. So we get this whole thing done. And you see that there's a certain non-terminal. So whatever symbol that we will see is right here. It may be followed by this, or it may create a new rule and have such symbols. So by doing this, we can create a table here. We can create a table here. What symbol we should see and what next a non-terminal we should go to. Okay. What we based on the rule and the symbol we can predict that. Okay. So basically, this one we actually taking the set. So this one we actually taking the set element and we can create a rule. Okay, create a rule and create a different set rules. Okay, and by doing that, we actually create the first follow set for the whole language. Okay, and then we can use that to build a table. So this conclude my talk on the LL1 parsing and for the table-driven for predictive parsing. Okay. Next one, we are moving on to the LR parsing. It is also table-driven, but it is using bottom-up parsing, and this is commonly used in the so-called flex bison way. Section 10, LR parsing, LR parser, and bottom-up parsing. Before we go into the LR parsing, let's actually review this LL parsing, table-driven parsing for a while. So basically, you have the token, say you have 1 plus 2, okay, parentheses, times 3. Okay, let's assume this is a token. So basically, we push in our symbol, okay, and we scan the symbol, and there's a certain table, the so-called follow set, predict set, whatever set they are, okay? So basically, we push in our symbol, okay? We push in our symbol, and then we process them. So basically, we may have the so-called, here we have a so-called factor, and then a plus, and then a factor, and then the rule fit. So the whole thing being evaluated to an expression, and the expression actually being popped out, and then you read another parenthesis. So the whole thing being evaluated again to another so-called turn, and the turn actually push in a star, and then another ID cofactor, and factor pop out as a turn, and turn actually pop out, time together, it becomes an expression, and you return. So basically, by doing this, when the rule is actually qualified, we pop out. When the rule qualified, that we pop out. So basically, you will build such a tree. You build such a tree as you will have 1. Okay, you will have 1. 1 is actually a number. So number will be a factor. Okay, and then you have number as a factor, and factor and will be a turn. Factor will be a turn, and turn plus turn will be an expression. Expression putting the parentheses together. Okay, let's go down here. Putting the factor together, you become another factor. Factor will become another term. Okay, I'm sorry. Factor, okay, here it will be the factor. So expression, with parentheses that actually is a vector, and 3 is another vector. So vector times vector that become a term, and I'm sorry, that become another vector, okay? And vector will become a term, term become a expression. That's a top-level expression you get, okay? So basically, that's the parsing tree will be created based on this. And now depending on push pop and the follow set and the predict set, okay? So that's what we talked about in the previous section 6 to 9. Now we are looking into another style of the parsing that's called LR parsing. And LR parsing is bottom-up parsing. So it is using ship reduce method, okay, ship reduce push and pop method, okay, we call it LR parsing. There are a number of variants for these, okay, but they all use the same driver. Driver means the main program, okay. They differ only on the table, how you generate the table, okay. So given a grammar, we want to develop a deterministic bottom-up method for parsing legal string, okay. And as in the top-down parsing, we do this with a table and driver. So it's similar way, just a different table. So LL parsing versus LR parsing grammar. So here, LR will always be bigger than LL. Okay, LL has limitation because of the left recursion and also the common prefix, okay, common prefix factorization. So LL always lower than include by the same look ahead labels LR grammar. So LR grammar, you have LR0, LR, SLR1, LL, LALR1, LR1, and LRK. Okay, so this different grammar being listed down here. And content-free grammar including everything, but content-free grammar, as we say, is an order n cube algorithm. And we try to operate, we try to find a parser in the order linear time or order linear log n time, okay? So the relationship is like this, okay? We are dealing with the grammar of different type. So a bottom-up parser works by maintaining a forest of the partially created subtree. The so-called partially created subtree is like this. You basically, you have a, say you have a vector, and that vector maybe is an expression, and that expression actually has a tree. So somewhere you may have another vector, that may be another vector, and that vector can also be an expression, and that can be a subtree. So eventually, when you pop out the two subtree, somewhere may be connected together. So that's actually, you need to maintain the forest of partially completed subtree, and then eventually build up a whole tree, okay? And the root level is a tree you like. LR parser almost always table driven, okay? So that's the rule. Okay, so here is a symbol you input, and you use the LR parsing algorithm called driver. And instead of using the set, you have action and go to. Go to actually is a rule that actually called DFA, deterministic finite automata, okay? And you have a ship, reduce, accept, and error, 4 different actions that you may take. So it's an action and go to rules. So let's assume that we have this whole set on the left, also calculator. Expression equals expression plus term. Expression can be a term. A term can be a term time vector. Term can be a vector, and vector can be a parenthesis with expression, and vector can also be an ID. So these are actually the grammar we actually look at for this LR parser. So first thing is that we will create a table that is action and go-to set. Okay, action and go-to set. Action looking at your current state, and token look ahead, and they will be determine which state you will go to. Okay, so that's the table finally we will have. So now the key point is still be what is the table and how we actually work on the table. So before we look into the table, let's look at the driver. So driver read in the input and consulting the table, and the table for 4 different kind of the entry: shift, reduce, action, and error. So these 4 different possible action you will take. So there is an action table, and you have shift is S, R is reduced, okay? R is reduced, and then accept means that you finish, okay? And error means that you should not go there, okay? You should not go there. So these are different actions that you may take in such a table. Okay, so that's that. And your driver algorithm is like this. You actually initialize your state to be 0, and then appending end of input mark to the end. And every time you actually take a simple while action is not a set and while action is not error, you do the following. You take in your stack, you have your stack, and you actually take in the input. So you compare your stack and your input based on your stack condition and input condition, find out your action, and then with some number, and then combining the state machine and the input. That's called configuration state machine, okay? Configuration state machine. That actually will take this, and you keep doing this to take different action. Okay, so let's look at this example here. Okay, so we have such a table. We have such a table like this. Okay, here we actually there's a set of the LR table. Okay, so this we have the sometimes we have a B. B is shift and reduce, but in this example we do not have the shift reduce. We break them into 2 separate rules. Okay, but in official one they may be shift reduce and shift reduce B type. Okay, but this one we don't have the B type. So let's look at first thing is that we start with a stack equal 0. The input is A times B plus C, and put in a end of input sign. Okay, that's a step 1. Step 2, we still in state 0. Okay, we still 0. We actually find a ID. ID is A, so we will take action S5. S5 is actually shift, so we will push the A into the stack. Okay, push ID and 5. You will push ID and 5. That actually is shifting. Shifting is push. Will actually shift the ID. ID is A and 5. That's action S5 action. We push that and 5 into your stack. After that, we go to the state number 5. Our state is number 5. Okay, go to state number 5, then basically we go to step 3. We actually, with the ID and 5, we look at the star now. So star is saying reduce 6, reduce 6. So action is reduce 6. So we actually pop out your ID and 5. So ID and 5 pop out. So we kind of creating a subtree of 5 that actually is a ID. So that's a subtree that we determined already. Okay, and with that actually we push in this one. We reduce. So actually that actually with a 6. Okay, 6 we kind of actually reduce action 6 with the time, so that we determine that actually is a factor, and number 6, reduce 6. Reduce 6 will use a go to, actually is a factor 3. Is a factor 3. So factor 3 is the ID 5. Okay, that's actually, it's ID 5. So that's actually, we'll go to the ID 5. Okay, that actually factor 3. Okay, reduce 6, the reduce, and because you are actually have the state 0. So state 0 and actually reduce 6, you actually have the factor 3. Okay, factor 3 like this. So we push in the factor 3 based on state 0. You pop out these 2 things, you have 0, and then you reduce to factor 3. So you push in the factor 3. Okay, And factor 3, you go to the state 3. So go to the state 3. State 3 means that reduce 4. Reduce 4, you go to your state right now. You reduce 4. Reduce 4, you go back to the state 0. State 0, you actually go to terminal turn 2. Okay, turn 2. Turn 2, okay, turn 2 is actually, so turn 2 that it determine the turn. Okay, so by doing this, you actually do step by step, you will be the following. So that's a continue. Okay, so turn 2, you finish. Okay, turn 2, you finish. And then you actually have turn 2. Okay, turn 2, and then you push in. The next one is actually star. Okay, you push in the star, and you go to this one called S7. Okay, the state 2, S7. S7, you will go to, you actually will continue. Okay, you have state 2, you go to S7. And the next one, you will continue to see. Next one is, you will see a parenthesis that's saying S4. Okay, S4. You see a parenthesis say S4. Okay, S4. So you actually push. S is shifting, so your 4 being pushed in. Your 4 being pushed in, then next one you actually determine this 4 actually is an ID, is a vector, is a term. So these are also always a processing the 4. So the 4 being processed, okay, then you start to look at the plus sign. So you look at the plus sign. When you look at the plus sign, it actually is doing S6, plus sign S6. You reduce 6, and you do reduce 6, reduce 4, reduce 2, and then you go to this one, okay, shift 6. So something like that, okay, you trace it step by step, and eventually you will finish the whole table. So basically this, the so-called LR parsing, it really depends on a precompiled table, okay, precompiled table for you. And there is the next day and the action the next day combination of each rules. Okay, so that's that. And that's you will eventually go to the accept state. Okay. Okay, so let's look at this calculator language example. So we get such things, okay, epsilon, and we have the input called A comma B comma C semicolon. Okay, so we get started ID A, so reading A, and then that actually is an ID and followed by comma, and then ID B followed by comma, and then ID C followed by a semicolon. So at this moment, we just keep pushing it until we see a semicolon, and that actually is an ID list tail. Okay, so IDC with ID list tail that become another ID list tail, and IDB with ID list tail that become another ID list tail, and IDA with ID list tail that actually become the ID with list. Okay, that's that. Okay, so that's a button-up grammar for calculation rules. And here we actually figure 2.235 grammar is like this, okay? And we actually can combine them into 2.16, okay? Actually, it's from 2.16, it's bent into the Pluto 2.25 that don't have the option. So each rule being written separately. Okay, let's go back to look at this one called sum and average program. Okay, sum and average program. So we have the different production rule. Let's actually model the parsing process with this sum and average program. Okay, so we start with the program. Okay, start with the program, and program start with the statement list and the end of program. A statement list, there is the breakdown. Breakdown is the current cursor. Okay, it's a current cursor. Okay, so this one we have a different current cursor. It's called closure. Okay, and with that, actually we read A. So read A, we will actually read A will push in a statement, and statement will push in read, and then push in A, and read A actually finish the statement. So we pop out the statement, and pop out the statement, and then we push in the statement list. Okay, so there is a statement with statement list, and the statement list pointing to statement. So by doing that, we actually do read in one by one to, so the start square means where the cursor is. So every time we trace to the different row and go push pop, and then build a tree, and based on the different shift and shift reduce rules. Okay, and based on those tables. So right here we do have the bigger action table and go-to table for our calculator languages. Okay, for our calculator languages. This one is shown in figure 2.26 of your textbook. Okay, and in the middle you see that actually every rule that has transition and go-to, stay, and set. Okay, and each grammar rule being written down in this way. So that whole thing actually can be characterized as a configuration state machine. Okay, CFSM, and that is such a state machine. Okay, and such a state machine mapping into the table that is. Okay, this one is a complicated version of this table. Okay, of this table. So basically, from your grammar rule, okay, from grammar rule, you do step-by-step traversal. You do your step-by-step traversal like this. You will generate your state transition table like this. Okay, and eventually you have your driver and your table. You should be able to do parsing for the whole language you have. Okay, for the whole language you have. And this is a driver for table-driven LSR parser that we actually see. Okay, so LR parsing is actually can be done automatically, and the so-called Bison and the Bison and the Flex is an example of LR parsing. Okay, so parsing variant, you have LR0, LR1, SLR, and LALR. And these are different way of doing LR parsing. That's actually deeper in the grammar. Okay, so when you design a grammar, it will be different. And we call this the CFSM as characteristic finite state machine, okay, for the configuration. So each parser has its own configuration grammar, and that grammar set has a state machine, and the state machine being mapped into the so-called table here, and the table being used in your parser, LR parser. So LR parser is using the so-called shift reduce diagram, passing through each statement rule, and then you will generate the required next state and data, okay, and creating the rule that is. Okay, and there are several variants for the LR parsers. Okay, the button-up parsing table, okay, like the table-driven L1 parser, these are different as LR parsers. It kills a loop in the driver, okay, and then inspecting the 2D table to determine which action to take and which go to the next state. So shift table entry indicate that state should be pushed. Reduce is pop out, okay, and build a subtree, okay. So there are some epsilon production need to be handled as well. This one, we don't spend too much time on it. Okay, there's some epsilon production you need to take care as well. So this is the end of the chapter 9A, our lecture 12, the theoretical parser. Okay, theoretical parser. And in this lecture, we basically go through recursive descent parser, okay, and also two different ways of doing table-driven parser, one in LL grammar and the other one in LR grammar. And this different kind of the parser, they all work, but they will work in different way. And building this different parser will take different technology. Okay, thank you. Bye now.